Hello, welcome to my Baptronics lab here in Black Hawk, Colorado, up in the mountains. And today I want to talk about a Decavider. Used to be made by ESI. I think it's ITI now that makes these, but this is a model RV622. It's a 6-decade Kelvin Varley Voltage Divider. So we're going to talk a little bit about what is a Kelvin Varley divider and kind of a little about how they work and what are they used for. This particular unit, before we get started, it was a rack mount unit. Was just a metal case with flanges, no feet, no nothing. I didn't particularly like that myself. I wanted to have something that moved around on my bench a little easier without scratching it. So, and I also wanted something that just looked a little bit better. So I made myself a little wooden case for it and stained it. As you can see, it turned out relatively nice. There are feet, rubber feet underneath. You can see the metal case there. And just makes it a little bit more pleasant to use. So let's see, what is a decade voltage divider? Well, if you provide an input voltage that is very precise, and let's say in this case it's a 10 volt input, and I've got that input. I know that it's 10 point. Let's take her down to 4 zeros, so that we're down in the 10,000th of a volt range, or 100 millivolt, 100 microvolt range. Anyway, provide that on the input, and then for every turn of a dial, you will reduce by a factor of 1/10 of that dial the value of the voltage coming out on the output. So rather quickly, I have 10 volts coming in on here, and I'm showing that I'm getting 10 volts out within 2/10,000ths of a volt. And if I was to turn the dial on my first decade one notch, I'll see the first digit drop from 9 to 8. So I went from 9.9998, which were essentially 10 volts, to 8.9997, which is essentially 9 volts, to within the 10,000th range. So at least within the first 3 decimal places, I'm accurately dividing this down. So let's take her down one more step. And we went 7. So that's the basic function. And every one of these dials will affect the next digit, next decimal point, the same way. Turn them down one notch, you're going to see it drop one. So then you see, well, okay, that's interesting. What do you use that for? Well, it is the basis for a lot of voltage calibration equipment. Provide a very accurate input voltage and provide a high resistance output. That's another one of the disclaimers of the Kelvin Varley circuit. You want the output to affect the resistor network that's within this thing very little. Okay, well, when I'm using the Kelvin Varley divider this way, I'm looking at all 9s right now on my 6 decades. 0.99999. And I multiply that times whatever the voltage coming in is. So let's assume I've got 1 volt coming in. Then essentially I've got 1 volt going to come out because I'm going to get 0.999999 times that voltage coming in, coming out. So let's, then if I step it down, then I'm going to be taking 0.899999 or zero point 0.7 or whatever. And if I was to take the next decade, I'd be going 0.889999 times my voltage in would be my voltage out. Okay, I've decided to tear down the casing and show you the internals of the Kelvin divider. I've made some measurements. I did clean all of the wafer switches very carefully with some switch cleaning fluid and some Q-tips. I was careful not to get any debris onto the contacts or anything. But my measurements indicated that this is the most significant figure here. This would be the 1s through 10. And there are 11 resistors on this, which would be part of the traditional Kelvin pattern. They are all 100 ohm resistors. The second decade utilizes 11 resistors as well. They appear to be 20 ohms apiece. The next decade, though, has 12 resistances, 12 resistors in it, and as do the next 3 decades. And then the final decade only has 11. Well, now that we've taken a look at the interior of the divider, the Kelvin Varley divider, let's take a look at the circuit. I've drawn what I believe to be the circuit and values that are in the inside of this Kelvin Varley divider, this RV622. And let's start off with what we all know probably if you're even a fledgling electronics enthusiast. You've got a divider string of resistors with a voltage across it. If the resistors in the string are all equal in resistance, then you're going to have an equal voltage drop across each one. And if there were 10 of those resistors and I tapped off of each one of the 10, I could go from 0 to full voltage in 1/10 increments. So that's how we start out here with this Kelvin Varley. But, well, let's first of all show us, in this particular unit, this RV622, we have 1,000 ohms of input resistance. So they've used 10 100 ohm resistors. Actually, they used more, but they used 10, we'll say, and that would give me 1,000 ohms. They actually used 11. And you say, well, that can't be right. But it is. And it's a neat little trick that this Lord Kelvin came up with. Man was a genius. It took me a while to figure out what he did, but he threw an 11th resistor of equal value into the string. So I have 11 of these 100 ohm resistors. And then, for the next decade, he would parallel 2 of those resistors with the next decade. Then you say, well, why did he do that? Well, he knew that 11 resistors here wasn't going to cut it for a decade unit. So he needs to make the 2 resistors appear to be 1. How do you do that? Well, you parallel a resistance equal to those 2 resistors, and in effect you have a resistance equal to the value of one of the others. So if we have 200 ohms here and all of the other resistors are 100 ohms apiece, we want these 2 100 ohm resistors with a total of 200 ohms to now look like 100. So how do we do that? Well, you parallel another 200 ohm resistor off of it. Total resistance is 100 ohms, so this appears to be 1 resistor. And you put your switch unit such that you jumper over, you go 2 resistors at a time as you go up and down the scale. The resistance in the next decade we know now has to equal 200 ohms in this case. And if I'm a decade, 10 resistors into 200 ohms means each one of these resistors has to be 20 ohms in value. And they're 20 ohms, I verified that. But we're not done wanting to come up with other decades. So we want to kind of do the same trick we just did here. It was pretty neat. So that's what he did. He says, okay, I'm going to put an 11th 20 ohm resistor in here. I'm going to jumper 2 resistors at a time as I use my switch and go up the scale. And I'm going to determine what my resistance value has to be in order to make the 40 ohms of resistance that these 2 resistors create equal to 20 ohms, so that it looks like one resistor, and I only have 10 resistors then in the chain. Well, 10 resistors in the next decade have to equal 40 ohms, so that I would require 10 4 ohm resistors in this next decade in order to parallel that 40 ohms and turn it into 20. And then in the next decade, I would do the same thing. I would take the 2 4 ohm resistors and I would come up with a value divided by 10. So 8 divided by 10 would be 8/10. I'd have to have 10.8 ohm resistors in a chain in order to make the 8 ohms appear to be 4, and so on. However, there's another trick that we learn here. Inside this particular unit, we don't have, in the third decade, we don't have 4 ohm resistors. We use the 20s again. In fact, we use the 20s in every decade after that. Well, how can they do that? Well, when you have a string of resistors forming a divider, and they're all equal in resistance, then as you go up and down, you're going to get an equal voltage on each one, regardless of what voltage is on there. Okay? But what I need to do is I need to make this chain of resistance equal to the previous chain's value of 2 resistors. So I needed to, in the second decade, I had 2 20 ohm resistors in series. That's 40 ohms. And I know I need to come up with a chain of resistors here that's equal to 40 ohms. That's why I said I needed 10 4 ohm resistors. But if I'm going to use 20s, that gives me a 200 ohm resistance in this chain. How do I make that 200 ohm resistance appear to be 40? Well, I parallel another resistor across that entire chain. Find a value that makes it equal to 40. And that happens to be 50 ohms. So they got a 50 ohm resistor across this third decade. And they do it again in the fourth and the fifth and the sixth. So that's the little trick they use. They were able to use the same resistance values all the way down, so they only have to manufacture one value, and then they come up with a parallel resistance to make that work, and the divider still divides it out, so we're good. So in every chain after that, that's what we've got. We've got a 50 ohm resistance in parallel with a string of 11 20 ohm resistors, and we're picking off 2 at a time, and we're coming up with equal resistance right down until we get to the last decade. And here we're not going to bring off any more decades, so we don't need that 11th resistor. We need 10 in the chain, and that's what they did. But they're still using 20 ohm resistances down here, and they had to parallel that chain of 10 20 ohmers off of a string of 2 20s here, so you had 40 ohms. So we want this to be 40, so again they use that 50 ohm resistor. And that's it. And then they picked off the voltage at the end. When you reference to the negative side of the battery and off of the first chain, you come across, there's fine, and then you're taking a look at what's coming off of the string of chains, you're picking off where this lower switch is. You're picking off the value that's there. So like if we had 0, 1, 2, 3, 4, we're going to see the 0.4 times whatever voltage was on that chain is what's going to be passed along to the output. Then the next string sees what's across voltages across this resistance here, which is now one resistance equal to 100 ohms. It's 1/10 of the value coming in. So I've got 1/10 of the total value on the first string on the second, and I divide it out. I can pick whatever I want, and then I've got 1/10 of that second coming into the third, and another 1/10 to the fourth, and a 1/10 to the fifth, and so on. Well, in the end, when you've applied your reference voltage to the input, and you've put your voltages through here, and you make sure that you have an extremely high load on the output, extremely high Z, high impedance load. In my demonstration, I use this Fluke 8520A, that's the top voltmeter unit. That voltmeter has a 10,000 megohm input impedance, so 10 gigohms. It's a very, very high impedance. So I felt, with 10 gigaohms compared to 1,000 ohms, I feel relatively confident that I'm not loading this circuit at all, and I'm allowing the voltages to be divided as we describe here in this little demo. Well, when I do that, I can come up with a circuit that is equivalent. And to me, normally they would talk about the divider being equivalent to a potentiometer, and that's true. But if you think about it with the load voltage on there, and then no current flow through because we've got a high impedance load, and when what we're doing with each of the switches in the decades, essentially we have, for every decade, we have a voltage source. A selectable voltage source, 10 steps. So in every one of these decades, you've got 10 steps of voltage, equal steps. So like in my first one here, I go from 0 to 1, which I can multiply by the voltage of the reference voltage, and I can do that in steps of 0.1, 1/10 of whatever the incoming voltage is every step. In the second decade, I've got, I go from 0 to 1/10 of A, and I can do it in steps of 100th. In the third decade, I can go from 0 to 100th of whatever the incoming voltage is, and I do it in steps of 1,000, and so on, right on down to the last decade, where I can go from 0 to 10 10 millionths, okay, there we go, times the incoming voltage, in steps of 1 millionth at a step. So if I've got 10 volts on here, I can resolve that all the way down to a microvolt using this system. And if all of the resistances were exactly as they were supposed to be, exactly equal to one another, and uninfluenced by any of the resistance in the switches, and there's no potentials developed by dissimilar metals and temperature fluctuations and things like that, then I'm going to have a perfect reference right down to a millionth of whatever my my precision voltage coming in is. These things, they find usage in the metrology lab. If you were wanting to provide precision voltages, you, like we did here, you would indicate or apply a precision voltage on the input, and you could divide it down to the least significant figure of the decades, and then use that for calibration of meters, measurement of data. It could apply to a nulling unit where you've got another voltage with a null indicator around it that you're bumping up against this, and when you've achieved null, you have zero current flow, and you'll know what your voltage is. Another thing is this is basically, if you think about it, I have a manually set digital to analog converter unit. So I can choose whatever voltage I intend the analog output to be. I can set on the dials, and I'm going to get it. If I was to replace the manual interface with an electronic interface, I have a D to A converter. And in fact, they have devised D to A systems that do just that. The circuit found its way into the D to A circuits that we have today. So for a fellow like me, having one of these on the bench means that I could provide a relatively inexpensive way for myself to calibrate my high impedance voltmeters, and then I can use my calibrated voltmeters to calibrate other meters on my bench. And I'm sure there's scads of other projects that could be derived from this, but so that's how this particular unit works in the Kelvin Varley system. Mr. Kelvin's a genius. I'll give him that. I don't know how he came up with this, but very thoughtful. And okay, well, I've run a series of tests, and I've concluded that the first decade of this divider is a factor of 10 worse than the linearity that's rated. So we're rated at 10 part per million, and I think on the first decade we're really more like 100 part per million. Now, that's not to say that it doesn't divide and that it's not actually a very good divider for a great many cases, but at least in the usage of the first decade, you're not meeting the original specs as far as I can tell, and I wouldn't try and pawn it off that way. However, as you go down the decades, if you zero out the first decade and then work down, you get progressively better until by the third decade you're running better than the original spec. But let me give you an example of what I mean by this. Right now, I've got all 9s on my divider. I've got 1 volt coming in from a precision voltage source. It's a Fluke 343A voltage source. So I've got 1 volt coming in, all 9s on the divider. Let's start stepping it down. So here's 8999. So I'm accurate to the 10th of a millivolt. 7, 6, 5, 4, 3, 2, 1. Okay, and now we've zeroed out the first decade. We have 0.099999 on the display, and we're getting 0.1. So let's go ahead and step down the next decade. So 9 to 8. So 89999 is essentially 0.09 volts. 7, 9999 is 0.08. Okay, I go to 6, and I'm 0.07 volts. 5 is 0.06, 4 is 0.05, 3 is 0.04, 2 is 0.03, 1 is 0.02. Let's go ahead and give ourselves another decade of range here. We are getting into the position where, you know, we picked up a whole nother decade of accuracy here. So we are now 19999, and we are showing 0.01999. So we are now in the tens of microvolts as far as being accurate. So let's see, we'll go 0, and then working on my third decade, I go from 9 to 8, 7, 6, 5, 4, 3, 2, 1, 0. Fourth decade from 9 to 8, 7, 6, 5, 4, 3, 2, 1, 0. My fifth decade, excuse me, from 9 to 8, 7, 6, 5, 4, 3, 2, 1, 0. And let's go to our next step. Let's go reduce the range again, and I have 5 microvolts that I'm showing. If I go from 9 to 8, I'm showing 4. From 8 to 7, I show 3. 7 to 6, I show 1, 2. We'll say 2. Yeah. All right. So 5, we're showing 0. 4, we go in -1. 3, we go in -2, I guess. 2, -3. 1, -4, and then 0. We're getting a -5 microvolts. Let's check something here. If I pull out my voltage source, plug in a short, and I am showing a -6 microvolts even with a short, 6, 7 with a short. So my meter is out of calibration by 7 microvolts. So we were seeing the microvolt decade changing the digit. So I go from 2 to 3, 4, 5, 6, 7, 8, 9. So we see it resolving the digit. We just didn't see the digit we expected, and that's partially the fault of my meter. So the decade divider is definitely dividing. It works well. I think it's within its linearity specs, using the latter half of the second decade and then going down. The first decade, I'm seeing linearity that's about 10 times worse than stated. So instead of 0.001%, I'm seeing 0.01%. That's what I think. Still very usable, worked very well. If you want the case, great. If you don't want the case, you don't want to pay the shipping on it, you don't need it, I can pull the case off, you don't need to take it, and you'll save on the shipping. Guess that's about it. Happy bidding. I'll send you the my diagram of the unit and my test results also. So, thank you for listening. Bye.